Hi everyone, great to be here in this micro experiment of how overpopulation and global warming work together. I mean, you'd think in a city hall you'd have a bigger room, but it's still 10 times bigger than my apartment in London and probably costs 10 times less. Okay, so to jump right in. My talk will consist of two main cats. We'll have a theory cat and a practice cat. So first I'll be giving a slight introduction to neural networks. It will require some previous experience with machine learning, but not too much. And then I'll dive into convolutional neural networks as a deep learning architecture. And then there will be a practice part with TensorFlow and some actual TensorFlow code. Then some quick background about me. I just finished first year computer science in Munich, at the University of Munich. And I'm currently doing a semester off interning at Google right now in London and at Bloomberg after. And I started with machine learning about 6 months ago with probably the coolest seminar topic ever, deep learning with TensorFlow, and wrote a paper which was supposed to be 5 to 6 pages. I ended up writing 16 pages. So if you want to know more about TensorFlow, I do really recommend it from a very objective point of view. Then jumping right in, I think from a very simplistic view, any machine learning problem can be reduced to two main components. We have some observation or feature X we make about the world, and some truth Y we want to extract from that observation. And because the world is a pretty exciting multifaceted place, we'll usually have more than one observation. And while all observations are equal, some are more equal than others. And there's also usually more than one side to a story. And in the end, it turns out that there is, of course, only one actual truth. So now to take this from the narrative to the scientific, what we have here is a very basic neural network where we're mapping some input vector X to some output scores Y by applying an affine transformation, which means we multiply it by a weight matrix and add some biases. And at the end, we would usually compare this to some label vector Y hat. And to move from this basic neural network to a deep neural network, it doesn't really take all that much. Again, we have our input layer and our output layer. We connect each input feature to all the neurons, as by the nature of a fully connected neural network. We add weights. We do that for all the neurons, and then we start adding hidden layers. And in these hidden layers, we have nonlinear activation functions, which make our model learn more complex things rather than just linear functions. And then to make it deep, we add some more hidden layers. But of course, I mean, there's more to deep learning than just adding hidden layers. And there's actually a very fundamental and essential reason why adding hidden layers makes a lot of sense for lots of tasks in machine learning. And that is the fundamental assumption of deep learning, which assumes that data is structured hierarchically. That is, whatever our data is, be it speech or be it text or be it an image, can be decomposed into smaller and ever smaller units, and then so that early layers can pick up those atomic units, and later layers can then combine those to have a more complex and abstract object, such as going from simple pixels or just numbers to the face of a human. And of course, if that just went way over your head, there's also your employer's view of deep learning. Just maps data into profit by 21st century magic. And so one thing we often use machine learning or deep learning for is image classification. So if we take this image, and vegetarians, please close your eyes right now. Then of course an image is really nothing else than a collection of pixels. You can close your open your eyes again. If you still see the cheeseburger, I'm sorry for having traumatized you. And of course, the computer, a collection of pixels, is nothing else than numbers. And more precisely, if we have a color image, our image will really be consisting of 3 separate channels: a red channel, a green channel, and a blue channel. So that's what our data is. And in image classification, what we usually want to do is classify an image into one of 8 classes. So we have an image, and we want to find out if it's a cat, a unicorn, or a chainsaw. And by the nature of deep learning, we want to use this basic assumption that our data is structured hierarchically. That is, we want to extract hierarchical features. So we might start out by just recognizing edges, so the very basic unit of an image. And then combining those edges into contours, and those contours into parts. So maybe a nose, or an eye, or an ear. And then combining those already quite complex objects into the final and most complex targets that we want, which are actual objects. For example, the face of a human. And first of all, we might ask, why reinvent the wheel? So we already know what fully connected neural networks are. We already know that deep learning turns data into profit. So why do we need anything new for this at all? I mean, if you think about it, we could just take an image, we just flatten it out, and then we feed it into a regular neural network. That is, we add hidden layers, we connect each pixel fully, so that means to each and every neuron. We do that for all the pixels, and then we add more hidden layers, and more hidden layers. And at the end, we'll have some output nodes, and those represent the scores that tell us how likely it is or not that the input image is, for example, a unicorn, a teapot, or a car. And to understand why, I mean, first of all, this would work. There's absolutely nothing wrong with this model at all. But to understand why we need a different kind of approach to this, we need to talk about this kitten. So if you look at this kitten, you can see that it has two eyes centered quite centrally here in this image. And on the next picture, you can also still see a cat, but it's deformed. So this is not a boomerang; it actually is a cat. And you can still see that it has eyes. I mean, it's easy for us humans, but the eyes look a bit different, and they're also not in the exact same spot. So if a fully connected neural network were to learn to recognize eyes, it would have to learn to recognize eyes exactly in that location that look exactly like that. And also on this salad cat here, we still see it has eyes. It's easy for us to recognize this. But they're again in a different position, which means to the neural network it's completely new data, and they also look kind of different. And lastly, in this image, we can really see that on this image we have three different sets of eyes, and with a regular neural network, a single neuron would have to detect eyes in the center, and another one would have to detect eyes to the right, and another one to the left. So if you think about it, if one neuron already knows to detect eyes, to combine the edges and the pupils and tell us that it is an eye, wouldn't it make sense that to reuse that information that neuron has learned in other places of the image? And this is the basic concept of convolutional neural networks, and it's called weight sharing. This is what I'll go more into now. So the idea is, if we have an image and a neuron, then we would simply connect the neuron to a single part of the image, which is called the receptive field. And again, if this image now learns to recognize an eye, then rather than have it relearn everything it already knows in a different part of the image, what we do is just slide it to the right. And then it can reuse its information there and learn to detect eyes again in that corner. And then we can slide it to the bottom and then slide it to the right. And now to move more into the mechanics of this, what we're actually doing, if we have a grayscale image like this, then again this is just a collection of pixels, and this neuron that I just showed you is what we call the kernel or filter. So what you see here are the weights of that neuron, and the sliding process is nothing else than simply plopping that kernel onto the image, and then computing a quasi-dot product. So we just multiply the weights with the respective pixels, and then output a single value. And this process, to be technical, is called a convolution. And then, just as before, we slide the kernel across the image, produce a new output, slide it across, and produce more and more outputs. And this would be a single convolutional pass in a convolutional layer of a continent, as they're called for short. And to put this into 3D, again, I mentioned before, most images that we're dealing with are color images. So this single patch I just showed you in a 3D world is nothing else in the box. And just like before, we slide this box across the image and produce a single output pixel. And then we slide it across more and more, and each time we compress that volume into a single pixel. And now you can imagine that if we slide that box down by one pixel and move it across and do that for every single row, what we get at the end is a single output volume. And again, this output volume is just produced by only one neuron. And then if you use another neuron and do that same process again, you get more output layers, and so on. And this is what a single layer in a convolutional neural network would do. We have several such neurons, and each neuron simply gets fed the entire image and produces one such output layer. Now, to sum this up, what we have here is, for a recipe for a convolutional layer, is an image with dimensions with a width, a height, and a depth. And then this kernel that I just showed you, or also called filter, with other dimensions k, l, and n, where the m, so the depth of the kernel, will usually always be the depth of the image, so we just consume the entire depth. And where k and l will usually be a lot smaller than the image, so often we use like 5x5 convolutions or 3x3 convolutions. And so for the cooking part, you would then simply slide your image into an oven, or maybe not. You would slide the kernel across the image, as I showed you before, and then compute the dot product for each configuration. And that's a single layer in a convolutional neural. Now, the second part of any convolutional neural network is called pooling. And this is another layer. And what pooling helps us do is achieve translational invariance. And what this fancy word just means is that if you have an image then if you just shift it across by 1 pixel, theoretically that's an entirely new input. But it makes sense that if it's just shifted by a single pixel, then we don't have to relearn everything from scratch. And pooling, or more precisely max pooling, uses the property, or the observation that the maximum in a sequence always stays the maximum, no matter how you permutate it. So imagine this is an image, and you can see the maximum here is 66. And if we now slide the image by 1 pixel to the bottom, then theoretically this is entirely new input. But if we just look at the maximum, then the maximum has stayed the same. And also if we slide it to the right, again the maximum has stayed the same. So if we're just looking at the maxima, then this picture has not actually changed. And this means that to us we have achieved a kind of translational invariance. And again, what this means in practice is that if we have an image, we'll have a small patch, like a 2x2 patch, and then always just select the maximum pixel from that image. So we produce the 66 here, slide it across, and the 79, and 66 and 128. And again, the idea is if we just shift this image by a certain number of pixels, these maxima will not actually change at all, and that achieves kind of translational invariance. That's what we achieved, and also what you can see here is that it's downsampling. So in this case, we used a stride of 1, which means we did not, or each time we slid the kernel by a single pixel. If we actually slid it by the entire width of the kernel, then you can imagine that we would have picked 1 pixel of every 4, and thereby reduced the volume or the width and height of the image by 75%. And this is one way to reduce dimensionality in a convolutional neural network, because dimensionality means more weights, and that can quickly blow up our model. And next to max pooling, which I just showed you, there's also other pooling functions possible. So one other idea is to use average pooling. So we would actually pick the average of all those pixels, and that would be a kind of blurring the image. So that can also be of use. Now, finally, we can sum up this neural network architecture in this regular expression. So again, we have an input layer, and we'll have one or more of these constructs consisting of a convolutional layer. So sometimes we'll actually have more than one convolution behind each other. And then we'll have optionally also a pooling layer. And then we'll do that a few times. And lastly, what we usually do to make the higher level logic, we'll have some fully connected layers to produce the final output scores. And then we have the output layer. And that's basically it for the theory part of convolutional neural networks. Now I'll talk a bit more about TensorFlow and then show you how you can implement such a convolutional neural network in TensorFlow. So first of all, what is TensorFlow? It's an open source deep learning library that was released a little less than a year ago, in November 2015. And according to itself, or to the initial publication, it's especially suited to large-scale machine learning and heterogeneous distributed systems. So it's a lot of words, and I'm sure whoever came up with that name got a pretty big raise. But I'll show you that those words do actually end with things. So first of all, I'd like to talk about TensorFlow's computational paradigms. So just how TensorFlow approaches the task of machine learning as a whole, and what it does different from other deep learning libraries. And the most essential part of the deep learning, TensorFlow's computational model is a computational graph. And this is just simply, so you may know this from other computer science fields, it's just simply a declaration of a mathematical expression. So you can see that if we have two inputs, x and y, that we transform in some operation dots, then we draw directed edges from those inputs to the operation and annotate the operations with their name. And in this example right here, we have, for example, a simple logistic regression where at the end pops out of this tan h, which is the hyperbolic tangent, or that, which is a prediction. And in TensorFlow, there are three basic components to this computational graph. The first is operations. And first of all, in the graph, operations are the vertices or nodes. And very basically, an operation is any transformation or combination of 0 or more inputs to produce 0 or more outputs. And you can see from this very general definition of taking 0 or more inputs and producing 0 or more outputs, we have a very flexible interpretation of what an operation actually is. So of course, on the one hand, we have the basic mathematical definition of an operation, for example, the matrix multiplication, but then we can also have a variable be an operation. Because if you think about it, a variable is nothing else than an operation that takes 0 inputs and produces a single output corresponding to the state or variable that it holds. And on the other extreme, also a network communication port to have a single input but produce no visible output because it sends something over the wire. Then next to the operations, there are tensors. And first of all, from a mathematical perspective, a tensor is the generalization of two-dimensional matrices, one-dimensional vectors, and also zero-dimensional scalars. So it's just an n-dimensional, multi-dimensional array of fixed static type, so with homogeneous values. And in TensorFlow, what a tensor is a sort of symbolic handle to a single output of an operation. So that is, if we have our dot operation here, then the tensor would be an interface to compute that value. Because as you'll see later, when we program in TensorFlow, what we'll have is we'll be declaring our graph, but not actually executing it on the spot. So for that, we need a special session environment. And the tensor allows us to pass around data, and when we connect the tensor of the dot operation to that of the plus operation, we get a directed edge from the dot to the plus, and data will flow through the graph. And then lastly, there are variables, and variables, first of all, are operations. But what variables also allow us to do is store state in the model. So if you think about it, as soon as we computed the dot operation here and passed that output to the plus, there's no reason to keep the output of the dot still in memory. It just consumes a lot of memory. So over several iterations of our model, most buffers or most matrices that we allocate will not persist. But for certain values, we do need state. So most importantly, for the weights of our neural network. And as such, variables allow us to store states. They actually store in-memory buffers across several iterations. And then lastly, to tie it all together, we have a session environment. And the session environment just manages resource allocation and coordination of all the nodes in the graph. Then another really important part of TensorFlow is the execution model, because it's actually the only deep learning library that has one built in that comes out of the box. And the execution model in TensorFlow, first of all, consists of a client, which is you writing your model and you executing your model. And then in a multi-node or clustered environment, you have a master. And when you execute your graph via the run method, you communicate with the master. And the master will then coordinate one or more workers. And the worker is responsible for one or more devices. So in a multi-machine setup, you can imagine each worker being responsible for a single node in the cluster. And each worker then coordinates memory allocation and computations between several devices. And of course, the nice thing about TensorFlow is that you can run that same model on your machine without all these several devices and workers and masters, and then run this exact same code in a setup where you have such clusters, and it will all work automatically. And what you can also see here is that there are two dimensions to TensorFlow scalability. There's the device scalability, so you can have more than one device. You can have 2 CPUs and 2 GPUs on each node. And then there's also the machine scalability, where you can have more than one node in a cluster. And then what also comes built into TensorFlow, which is really great, is visualization tools. So deep learning deep neural networks have the tendency of being deep, and it's easy to drown in them. So for example, a reproduction of the Google conception model has more than 36,000 nodes. And also some LSTM, some recurrent neural networks, that have more than 15,000 nodes. So that's a lot to keep track of. So this here is actually the conception model. You can see it's quite deep. And to help us with this, TensorFlow has what is called TensorBoard built in directly. And that is a really awesome visualization tool, if Wi-Fi allows it, yes. So first of all, what TensorBoard has is this graph visualization. So you can see here a neural network. And the nice thing is that we have names, is that you can have name scopes, as they're called, which are basically groupings of certain parts of the graph. And then if I want more information on layer 1, I can expand this node to see that, for example, I have weights and whatever I need to know to debug my model. And next to this graph, there's also some what are called scalar summaries, which is just information I can keep about my model while it is running. And here for scalar values, and then this really pretty cool thing, which is distributions. So for example, if I want to keep track of the distribution of my weights, I can see how they progress here with a quasi-Gaussian distribution here. And this on the side is the iterations. I can also change it to relative time or timestamps. And the x and z axis here are the actual distribution. Okay. Now, how much time do you have left?
At least 10 minutes.
Okay, perfect. then we can move on to the walkthrough. We'll need it in minutes. So what I'll show you is called a Linux 5 architecture, which is a very basic convolutional neural network that was developed by Jan LeCun in 1998. So that's already a very long time ago. It was used to recognize handwritten digits, and it's kind of a beginner confidence. I hope your regular expression syntax is still up to scratch. So we'll have two conf and full layers here. Then jumping right in. Anyone see this? Okay, so I took a bit of an object-oriented approach here, but I'll start here. In TensorFlow, we first of all need to declare a graph. And actually, the interesting thing is that theoretically we don't have to do this, because in TensorFlow there's a lot of global state. So by default, there's always one global graph. And whenever you add operations to a graph, it's always done to the global graph. So you can create your own graphs if you want to, but then as you see down here, when I create the model, I actually have to register it as the global graph, and then I use TensorFlow's direct functions here to add things to the global graph. So there's not like an object-oriented approach here. But then to the actual model, what I do here is create two placeholders, and placeholders are variables that I need to replace when I run the model. So when I run the model up here, I'll talk about this later, you can see there's a feed dict, and what a feed dict is basically a mapping from nodes in the graph to input values that I want to replace those nodes with. And theoretically, I can replace any variable, but placeholders have to be replaced. And this is just a way of feeding data into the model. And then the first thing here will create our two convolutional layers. That means convolutions and pooling. And as you can see, TensorFlow is quite low level, and I already, just for this very basic thing, needed to create some utility methods. So for this reason, there actually exists some abstraction libraries on top of TensorFlow. So people from the industry will probably know Keras for piano, and there's pfLearn that does lots of this for TensorFlow. But to move in here, when I create a layer, what I want is a set of weights. So either for a fully connected layer, I'll want lots of neuron weights, and for any convolutional layer, I'll want weights for each output feature map that I'm creating. So here I create a new TensorFlow variable, and I initialize it with a truncated normal distribution, which is like a normal distribution, but if any value is picked from outside 2 standard deviations, it's just redrawn until it's in that window, which just ensures that the values are not too long. And here I create bias variables, and I also have to initialize a variable with a constant or with some value. And here I initialize it with a constant of 0.1, and the shape will be equal to the number of neurons that we have in that layer. And then I create such a layer, which is just a name tuple up here. And that gives us the first convolutional layers. And you can see that we'll be using 5 by 5 convolutions, so that's what we slide across the image. And because these images that I'm feeding it, which are handwritten digits, by the way, only are grayscale, they'll have only a single color channel, which is the one here. And we'll want to create 32 output channels from that first layer. And then when we have those 32 channels, in the second layer, I'm transforming them into 64 output channels. Then once I have the layers, I have to reshape these samples because I am actually getting them as vectors. So the images are 28 by 28 pixels big, and I'm getting them as 768 pixel vectors. So that's 28 times 28. But in this case, I really want them to be the actual quadratic images. So I reshape them here. And then I perform my convolutions and my pooling operations. And the nice thing is that TensorFlow has these two things built in. So we have this conf2d operation. And to this I feed in the input volume, which would be the image, first of all. And then my weights, which are what I just declared up here, and which are the kernel that I slide across. And TensorFlow will do the actual sliding across for us. And these strides tell TensorFlow by how many pixels to jump on each iteration. So actually, the first number here is how many images to slide. This is the batch index. And then here we have width, height, and depth. How many pixels to slide in each case. And padding tells TensorFlow to make the output volume have the same width and height as the input volume. Then after the convolutions, we have the pooling. And again, this is built into TensorFlow, which is very nice. Pooling, again, just we feed an input volume, And here I specify, it's max pooling already, I specify the size of the kernel that I'm sliding across, and then it will slide the kernel across and pick the maximum out of every 4 pixels and produce an output order. So that's for the first layer. Then I just do the exact same thing again for the second layer. And then after those 2 layers, if you remember the architecture here, we feed it into 2 fully connected layers, and they just flatten out the images again and produce our final output scores. So what this means is that I create new layers, and at this point the image is no longer 28 by 28, but it's actually 7 by 7. And the reason why is that we did 2 poolings. And as I mentioned before, pooling reduces, 2 by 2 pooling reduces the size by 75%. So 28 by 28 times 0.75 times 0.75 is 7 by 7, and 64 output channels. And then just flatten it out into a big vector, because I want to feed it into a fully connected layer. And that layer will have 1024 neurons. And after that hidden layer, I'll have my final output layer, which is the 4th layer, and that will produce our scores. Then once I flatten my image here, again 7 by 7 by 64, the -1 is the batch index, so that just stays the same. And then I propagate the model. And what propagating means is just performing a matrix multiplication. We take our input, we multiply it by the weights, just like on that very first technical slide, and then we add the biases. And optionally, we can also apply an activation function, which is a nonlinear function that makes our model learn more complex things. And in this case, I use the rectified linear unit, which, if you don't know, is basically the most ridiculous nonlinear function you could think of. It's just 0 for any negative number, and then x. And the nice thing is that it's nonlinear, so we can learn nonlinear things, but it's also very simple to compute gradients and keep track of. And then what I do here with dropout, that's a regularization technique, which regularization, first of all, that's finding a trade-off between making our model achieve high training accuracy, so be really good at our training data, but at the same time not fit too much to just our training data, because we want it to generalize to any kind of data we feed it. So that's regularization. And the way dropout achieves this is just simply on each iteration by turning off some neurons. And the idea is that what can happen is that some neurons in our model can attach or can rely very heavily on some input neurons. So by turning some of them off periodically, we can actually have our neurons learn alternative representations of what we feed it, rather than just having a really big weight on a certain neuron. So that's the dropout layer. And then again, we just propagate it, propagate those that first hidden layer into the output layer, and then we get our predictions. And the predictions, first of all, will just be random numbers, which we call scores, but they're really just random numbers. And in this case, we'll have 10 different output classes per image we feed it, which correspond to the 10 digits the image can be. And to turn that into a probability distribution, which sums to 1, and where every value is between 0 and 1, we use what is called the softmax function. And that's just a very fancy way of normalizing values. So you can imagine it as dividing each value by the sum, and just doing that in a bit more fancy way. And then finally, once we have these probabilities, we can take the argmax, so the highest probability, and choose that as the output prediction. And the last thing we have to do is create a loss function. And as a loss, we choose something called the cross entropy, which just measures how similar or dissimilar to probability distributions are. So on the one hand, we have the probabilities we computed, and on the other hand, we have our labels. And the labels for each image are one-hot encoded, which means they're a 10-dimensional vector with only zeros except for one index where we have a 1, which is the actual digit it represents. And then we can measure how similar or dissimilar these distributions are and get a loss. And now we get to the actual optimization process in TensorFlow, which involves instantiating an optimizer. In this specific case, we use an atom optimizer, which just has some tricks to it. But then what we do here is pass the loss tensor that we want to optimize to that optimizer, and it will do all the fancy derivatives for us and anything we don't want to care about. And then the last thing we do in our model is create some accuracy metrics. So here I find the true positives and false positives. So I just check where the predicted class is equal to the actual class. And then I take the mean of that. So we'll have lots, what we get from here is lots of 1s and 0s a 1 whenever we actually got the right output. And then taking the mean gives us a measure of how accurate we were. And what's important to note here is that when the interpreter runs through these lines, the code is not actually executed on the spot. Because TensorFlow has a declarative programming model, which means when I write this code, it's just added to the global graph. And to execute it, I need to enter my session environment. And this is what I do down here. So this is the actual training code where I'll have instantiate a session. And I pass it the graph that's from this network. And then, so this is just to initialize the variables, which has to be done. And then 10,000 times, I would create a new training batch, which means I would take, sorry?
Can you put the code a little bit higher?
Yes.
Yeah, thank you.
Yeah, sure. So which means I take 100 images and then I'll feed that into the network. And just the last thing here, what does feeding into the network mean in TensorFlow? It's right here. Yeah. So this here I just have an option of compute the accuracy metric or not, because I don't always want to do it. But the important thing here is the session.run, which I showed before. Here I pass what are called fetches, which are the tensors, so the nodes that I declared that I want to compute the value of. In this case, I want to run the optimize node because I want the model to train itself on the input data. And I also already mentioned the feed dict, so I feed the examples and the labels that I get from the batch into the model, and then run the optimization algorithm, and that outputs, and that will update our weights in hopefully a good way. And now, I'm not going to run the model here because it takes about an hour to train this model. But basically, this is what a typical TensorFlow model would look like. And if you want to try it out, there's a GitHub repo for this. Okay, I'll just finish up. Because I started with machine learning 6 months ago myself, I just want to share some resources if you want to get into it more yourself. So first of all, some MOOCs. The internet is quite full of those. There's the machine learning MOOC by Andrew Ng on Coursera, which I think many people might already be doing. It's okay. It's 7 years old, which in deep learning means like 13th century. So it has some things that are not quite as accurate anymore today, like in terms of activation functions, for example. But it's really good because it covers a broad range of topics, and neural networks is just one section, actually. Then what I really recommend is the deep learning course by Google, which was released along with TensorFlow. It really covers some awesome deep learning, like really deep learning topics, and it's great because it also has TensorFlow examples. So part of the marketing strategy, of course. And then there's also the nano degree, which costs $200. Then some websites. First of all, the first one, if you want to know more about deep learning, that is like the best resource you could ever go to. cola.github.io. That is some guy who just knows a lot of things and describes them in a fantastically non-scientific way. Then the second resource here is a course on convolutional neural networks by Andrei Koperty from Stanford, which also has lots of stuff on neural networks. And then Koperty's blog, a deep learning book, is a book released by MIT Press, which is like a super theoretical book if you really want to go deep into the math. And then Kaggle is a resource for programming computations for data scientists and machine learners. And lastly, TensorFlow, I really do recommend it because so TensorFlow was actually released, like there's a post-release project with documentation and tutorials and everything. So it's actually a really great resource. Then lastly, just to go meta here, so I'm from Munich and we have PyCon in Germany, and the organizers just asked me to spread the word. It's 29th to 30th of October in Munich. And there will be I'll be speaking again, and there are also other talks on machine learning and deep learning. And you can have my special code here, visit MOOC 16, which gives you 15% off if you want to go. And yeah, then just lastly, stay in touch. Here's my email, link in GitHub. You can snap me, of course, if you feel very 21st century. And yeah, and my talk, that's where you can find it. Or you can just ask me for it after. Okay, do we still have time?
You have 7 minutes for questions,
wow.
but so questions for Peter.
Yes.
So roughly how much training data, how many training examples would that neural network have taken to get
regional results?
I think with convolutional neural networks, first of all, the more the better. So it actually is one of those cases. And I think with 1 million examples are usually good. So that's about as much data you have in this network, which is called MNIST. So I think 1 million should be okay. If you have less, then there's ways around that. But usually more is a good idea. Yeah.
Does TensorFlow provide some cross-validation infrastructure for like splitting test and training data and that stuff? Or?
No, it doesn't have that per se. You would have to do that. I mean, it's quite focused on deep learning, I have to say, not as much on like more like data science oriented things. I mean, of course, it's part of machine learning, but it doesn't do like data stuff as much as it's
You said you were using a step function for the activation function and that made calculating the derivatives easy, whereas I would have thought that would mean there weren't any derivatives because it's 0 or infinite.
Oh, yeah, so, the rectified linear unit, I can actually just show that. Because it is quite, so this is the function. And yeah, so it's non-differentiable at 0 if you mean that.
Oh no, I thought you were using a step function. I misunderstood what you said.
Okay. So this is the rectified linear unit, and it's the activation function used in most hidden layers nowadays. So as you can see, it's 0 to the left, and otherwise the gradient, so the derivative is just 1 everywhere else. And yes, it's non-differentiable at 0, but because we have biases, it usually never gets 0 at all.
What do you see as what are you most excited about using TensorFlow for?
So I think one of the exciting things about TensorFlow is that it has distributed execution built in. So most other deep learning libraries have no built-in notion of more than one machine, and often more than one device, like you can run it on multiple GPUs, but not more than one machine. And I think, especially on Google scale, but also on personal scales, I think it's quite interesting to be able to just plop your code into any setup and it will just run on whatever devices you have. So I think that's quite cool. And otherwise, I don't see, so for other deep learning libraries, there's not that much TensorFlow can do yet. So I think if I were to recommend a library to start out with, it's the one I would recommend. Yes?
Keras now supports TensorFlow as a backend. What do you recommend? Using TensorFlow itself or Keras?
So if you want, so I would not recommend Keras for TensorFlow, and the reason why is that TensorFlow has its own abstraction library. I can actually just show this stuff very quickly here. So for example, you just saw lots of TensorFlow code, and with an abstraction library you can reduce it to something like this. So you just say what layers you want and just add them together. And Keras is a abstraction library for piano, and it has the option of actually switching the backend between TensorFlow and piano. But the reason why I wouldn't recommend it is that TF Learn is a lot more adjusted to TensorFlow. So it actually does all of the visualization code for you. You can just run your regular model, and because there are actually lots and lots of boilerplate associated with having it visualized as beautifully as before. So I think that would be the way to go. Yeah.
You said you can just say what layers you want. How do you know what layers you want?
Yeah, so that's still like it's a bit black magic in that sense. I would start with looking at what other people have done. So what other architectures use. In the end, it's a lot of trial and error associated with deep learning in general. So I try out another layer, maybe it works better. If not, then I do something else. So I can't give you a definite answer on that. But I would try out looking at some models that other people have built, like AlexNet, like LeNet right now. That should be a good starting point.
Could you not use deep learning to work out what layers?
Yeah, that's quite meta.
Right, thank you very much, Peter.